Hi, I'm David, and I'm one of the lecturers at the Maths Learning Centre at University of Adelaide, and this lecture is about differentiation, or derivatives. So, derivatives are a thing that we do to figure out information about a function. So I'm going to need to start by talking about functions first. Let me just put a big heading first. Differentiation. So let me just start with functions. Most of us have been used to functions for a while. A function is a rule that where you put things in and it spits things out, and every time you put the same thing in, the same thing comes out. So you can define them by just having a big list of what all the outputs are for all the possible inputs. But usually there's some sort of formula that when you put a number in, you do a calculation on using the formula, and that's how the number spits out. And we're used to certain kinds of representations of functions. And I'm going to be using two today, one that you might not be so familiar with and one that you'll be more familiar with. So one of the ideas, and it'd be easier to do with an example, is that if I have a function, usually it's written this way, so you have function f, it could be any letter or even a word, but function f of x, it's not f times x, will normally have a formula, like a half of x minus 3, for example, and you can use any formula you want. This formula allows us to calculate what the value of the function is at various points. So for example, if I write down what this is at various places, there's a number line for all the values of x, and I could sub that number into the formula and get various values for what the x works out to be. So for example, if I put 0 into the formula, I will get a half times 0 minus 3, which is negative 3. And if I put 1 into the formula, I'll get a half times 1, which is a half, minus 3, which is minus 2.5. And at 2, I'll get a half times 2 minus 3, which is minus 2. And then at 3, I'll get a half times 3 minus 3, which is minus 1.5. And at negative 1, I'll get a half times negative 1 minus 3, which is minus 3.5. And this should be minus 4. And so at every point I can figure out what the function value is. So these ones are f of x. Okay, so I can see that as I move along here, then the value of f of x is changing. So as I move forward 1, the value of f of x goes up by a half. And if I move forward another one, the value of f of x goes up by a half. And if I move forward another one, the value of f of x goes up by a half. And derivatives are all about that change, that if I change the x, how does the value of the function change? How quickly does it change when I move the x? So this is one picture of a function. It's not particularly useful at the moment because it's really just a list of numbers. So one way that you can organize this representation is to have the values of x and you have a point moving on the x-axis, like that, and then there is another line to show what the value of f of x is, and so here at 1 the value is minus 2.5. And as 1 moves forward here, this moves forward here. And it's a little easier to see this in an animated thing, so I'm going to switch over to the computer. And here is the formula, half of x minus 3. This is Desmos, which you can, or Desmos, you can pronounce it how you like, which you can look up, just Google it, and you can draw all sorts of cool things here. So this is my x, and as my x moves forward, my y moves forward as well, but much slower than my x is moving. So if my x moves forward 1, there's from minus 6 to minus 5, the y only moves forward a half, not the y. I call it y because normally you have an x and then you have the value that comes out, you normally call it y because it's the letter after x. If I move forward 1 from -5 to -4, the value on the red axis moves forward half, and so on. Okay? That's how it works. And I could put in any formula I wanted and see what happened. So what if I put in x squared minus 5x? As I move this along, whoop, I can't even see the value of the output yet. And now here it comes. It comes in and it gets more and more negative. And then, it starts to go forward again. And at different places, it's moving at different speeds. If I go forward here, it moves back. Forward here, 1. It moves back about 2. Forward here 1, it moves back quite a bit less. Forward here 1, it turned around, hardly moved at all. Forward here 1, it moves now going forward. So at different places it's going at different speeds. When we had the formula before, it always went at the same speed as I moved the blue point forward. Okay. So that's another way of thinking about how one function moves when the other one moves. And already we've seen that for some functions, if you move the x, then the f of x will move the same way every time. And for other functions, if you move the x, the f of x will move a different way every time. So there is one more way that we would normally draw a graph. So the other way of drawing what the function is doing is to go back to this one and interpret each of these numbers as a depth or a height. So if it's minus 4.5, we'll go down 4.5. This is minus 4, this is minus 3.5, this is minus 3. And we'll do them each as a height. So I'm just going to draw that. I'm going to make them closer together so that I can see them. So minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6, 7, etc. And normally what we'll do is we'll draw this line here. And so here at 3 it was at minus 4.5, which is down here. Here at minus 2, I reckon I can fit that all on the screen at the same time. Here at minus 2 it was at minus 4. Here at minus 1 it was at minus 3.5. And here is at 0 it was at minus 3. And it keeps going up. And I can fill out... so I think if I go half of 4 minus 3, it's still negative 1. Comes out here. Okay, I can connect up all those points because technically it's possible for me to sub in minus a half and 3/4 and 0.1. And I can fill in all of these, and this is what the graph would normally look like. This is called a graph, this one. The other ones don't really have names. And so now if I imagine moving my x forward a bit, then there's a point here which we can imagine moving along the curve. I'll do that in colour. So we can imagine the x moving forward a bit, and then this height moving up or down a bit. And this arrow here is this arrow here. This is called x, this is called y. So these are three ways of thinking about how when x moves, the function value moves. And I'm just going to switch over to the computer. So this is the same graph that we had before. I've just drawn it. And as the x moves forwards, the point moves along the graph. So the x moves forward 1, and the y will move up by half. Forward 1, up by half, forward 1, up by half, forward 1, up by half, and so on until it comes positive again. So all of those are ways of thinking about how functions work. Why don't I just pop in the function x squared minus 5x that I did before. So here we saw that as we move this way, the function value became more and more negative, and then it went positive again. And as I move this way, the same thing happens. I can see that it comes down this curve. The function value is getting lower and lower, and then it's getting higher and higher. So this is a traditional graph. That's how I would do it. And in the polynomials lecture, you would have expected that x squared should have a sort of a U shape like this. So what we want to know is, how do we keep track of, given how fast the x is moving, how fast the y value or the function value is moving when I move the x? And that's a good question, and it won't be the same in the same places. We saw that this function, when x was in different places, the value of the function moved at different speeds. And so we're going to need to find basically a formula that, based on what x is, how quickly is the other thing moving? Okay. So here's the problem. It's really great for functions like this. This is called, It's really great for functions like this. This is a straight line when I draw it as a graph here, and I know that for every time the x moves forwards, the y will move forward by the same amount every time. Not necessarily the same as the x moves, but certainly the same amount every time. So that is called the slope of the line normally. Okay, the slope of the line is how far up it or down it goes for every one across. Now, if I move it 2, then the y will go up or down twice as much as well. And so normally to calculate a slope, we figure out how far the y moves and we divide it by how far the x moves. And that's called a rate of change as well, because these graphs might be describing something. It might be describing how the temperature moves as time moves forward, or it might be describing how the population changes as time changes, or it might be describing literally what the height of a ball is when you throw it, or it might be describing, it might not have anything to do with time at all. It might be describing, for example, how many drownings there are based on, at a beach based on the temperature. Okay, so all of these sorts of things can be done, and we're interested in how quickly they move. Okay. Right. So let me just say something. Slope for linear functions, if you have something that's like f of x is ax plus b, then the slope is a. And every time you move x up by 1, the f of x will go up or down by a, depending on whether a is positive or negative. So changing increasing x by 1 changes f of x by a. Okay? And increasing x by 2 would change f of x by 2a. And increasing x by 3 would change f of x by 3a. And so for linear functions, it's very nice. It's right there in the formula. And this plus b doesn't really make a difference. If it started out higher, then it will be higher later as well. Okay? Cool. So we can actually figure this out just from knowing 2 points on the curve. So let me just do this. For example, if the function f of x equals ax plus b has f of 1 is 3 and f of 5 is 58, find a. Okay, we can figure out that from this information. So we know that every time the x goes up by 1, the f of x will change by a. And so if it goes up by 4, then the f of x should go up by 4 lots of a. So all I need to do is to figure out how much the f of x changes by and divide it by how much the x changes by. So I can say that the slope is the change in f divided by the change in y, in x. This is the Greek letter delta, and it stands for change in. The reason it's the Greek letter delta is because in Greek it makes a d sound like the English D does, and when it was originally invented they called it D, because it stands for difference in. Okay, so it's the change in f divided by the change in x. So between these 2 points, the change in f, well, it went from 58 to 1. Sorry, it went from 3 up to 58, which means that the change is 58 minus 3. And the x went from 1 up to 5, so the change in x is 5 minus 1. And so we get 58 minus 3, which is 55, divided by 4. Now, as a mathematician, I would probably prefer to leave that as a fraction. Most of the rest of us would like to know about how big that is. I know that 52 divided by 4 is 13, so it's 13 3/4. But it's important for me to leave it as a fraction if I need to. So I'm just going to put this in here. So A is equal to 55 over 4. Okay, so that means that I can put 55 over 4 in this position. It's technically possible for me to figure out what this B is as well, actually, because I have enough information to find it, and I'm just going to put it there incidentally, even though it's not something that's actually necessary to do at this stage. I can also find B. Since f of x is now equal to 55 on 4x plus b. And I know that f of 1 is supposed to be 3. So f of 1 is supposed to be 3. So when I sub in 1, I get 55 on 4 times 1 plus b. And when I sub in, and that's supposed to come out to the answer 3. And so b must be 3 minus 55 on 4, which is going to be a negative number. What was 55 on 4? It was about 13 3/4. So looks like I'm going to get minus 10 1/4. But I'm just going to do this properly. It would be easier if this was in quarters as well. So 3 is 12/4. Minus 55 on 4. 12 minus 55. Well, 55 minus 12 would be 43. So minus 43. And I was right. The 40 divided by 4 would be minus 10, and then we've got another minus 3/4. So actually f of x is 55 on 4x minus 43 on 4. And I should really just check to see if this is working. Just check. If this is the correct formula, then f of 5 should work out to 58. So let's see. F of 5 is 55 on 4 times 5 minus 43 on 4. And 55 times 5, well, 50 times 5 would be 250. 5 times 5 would be 25, so that's 275 on 4 minus 43 on 4. And 70 minus 40 would be 30, 232. Now 200 divided by 4 would be 50, and 32 divided by 4 would be 58, which is correct. Now, it wasn't actually necessary for me to do that. I just wanted to show you that it was possible to actually figure out the other one. The important bit for this story that we're telling today is this part here, where based on the fact that this y moves by 55 and the x moved by 4, I can divide them to figure out what the a must be. And I know that that works because if it was a straight line, a linear sort of function, every time I add 4 to x, that's going to add 4a to the answer because of the way that expanding things out works. Okay, so that's all well and good, but what does that mean for derivatives? Because David, you've already been talking for a while, and we haven't got to actual derivatives yet. Don't worry, we're getting there. So now we want to say, well, that's all well and good for a function that's something x plus or minus something, but what are we going to do when it's one of those other functions that's curved, that has different changes in y for when you have different changes in x? So you have the same change in x, but you're in different places, and so you get different changes in y. What are they going to be like? And so we're going to have to find a way of dealing with that. Well, we can certainly reuse this same sort of thinking here. We can still do this thing of the change in f compared to the change in x. We just know that it's not always going to work the same way if the x's are in different places, but we can still do that. And that's actually called an average rate of change. So if you have one quantity like x and another quantity like y that changes as a function of x, and usually the x is time, then the average rate of change is the change in the output divided by the change in the input. And that is just how much you think it changes on average between those 2 points. It doesn't exactly change by any of those speeds at any point, but it's about right. So the average rate of change, so this is a definition. So if y is a function of x, the average rate of change of y between x equals a and x equals b is, there's no symbol for it, I'm sorry, delta y over delta x, so the change in y over change in x, which is the same as, well, the change in y will be that, and the change in x will be that. And that's what the average rate of change is. So for example, suppose a population of rats was 600 rats 1 week ago and is 400 rats today, is the average rate of change of the rat population over this time. So that's the question, and the answer would be, well, why don't I just let P be the population of rats and T be time? P be population and T be time in days. Okay, so you should always tell the reader what your letters stand for if they're not already there. If I had been given this question by someone else, say in an assignment or in an exam, and they had told me that P stood for population, then I would have used P. But if they had told me that R stood for population of rats, I would have used R. You need to use whatever letters you're given, but otherwise you can make them yourself. Okay, and then the average of change would be the change in the population divided by the change in time. And the change in the population, well, it went from 600 to 400, so it went down 200. But I'm just going to do it properly. So it should be the new one minus the old one over the change in time, which went from 7 days minus 0 days. And so that'll be 200 divided by 7. And I ran out of space. That's annoying. So I'm just going to pop this on the next page. So moved in 7 days. So that's minus 200 over 7, which is approximately, I'll just get my calculator, minus 200. So there's a separate thing. Minus 200 divided by 7 is minus 28.57. Now that's probably needlessly precise for what we're trying to get at here. It was in hundreds to begin with, so I can probably round it off to 29. So that's telling me that this is rats per day, because the top was in rats and the bottom was in days. And so this is telling me that on average we're going to lose that many rats per day. So a decrease of approximately 29 rats per day. And it's always useful in one of these problems that has an applied context to tell the reader a nice sentence to finish it off. Okay. So that's average rate of change. And we can visualize what average rate of change looks like on the graph. So for us, for this picture, this is days and this is rats, and we have on day 0 the number of rats was 600, and on day 7 the number of rats was 400. So we can draw a graph of this in the traditional sense, and I don't really know what happened in between, but the slope of this line is the average rate of change. If I average this out over the 7 days, then every 1 day you go down about 29 rats. Okay, that's the general idea here. But it could be that this function here goes up and then down, or down and then up, or up, down, up, or mostly 600 and then quickly goes down to there. We have no idea what the function really looks like. All we know is what happens at these points. And that's the idea of the average rate of change. The best estimate we have for what the function is doing is assuming that it's a straight line. Okay. But it's not a straight line, is it? My function isn't a straight line, and I can't really be sure if after this it's going to continue in that way. If I had a formula for what this graph was looking like, I could draw a much more accurate picture, and if someone asked me, what do you think it's going to do after this, I could try and follow what the graph is doing. And so if I switch over to the computer screen, I can get a better handle on that. This is just a picture of what I was doing there on this graph. If I move these points to different places, I can see that the average slope is not necessarily always a good picture of what everything is doing in between, but that slope there is the average slope. If these 2 points are pretty close together, it's not too bad. That straight line is not the worst. It's not a particularly bad description of what this function is doing. I mean, if I zoom in a bit, I can see the difference between them, but if I'm out at this scale, no, it doesn't really look that different. And this is the whole idea of differentiation. The whole idea of differentiation is that if I'm very zoomed in, if I'm close to the function, if I only move it by a little bit, then the average rate of change is going to be pretty much the same as the real rate of change, because my function is nearly straight. And this is a much more funky version of this. If you look at this, I'll put a link to this in the video notes if you like. This is a graph. It's the graph of this wicked function here. And as I move this point on the graph, what will happen is this little zooming view window, it's a bit like a magnifying glass, will show me what's going on in this circle here. So over here it's sort of going up, and then there's a bump, and then it's sort of a low bump, and then a high bump, and then another low bump, and then it goes up. And so this is what it looks like. And already over on this side here, it looks pretty straight just here. Not so good just there. But if I zoom in a little bit further, it's actually pretty straight there too. And it's pretty straight in most places when I'm zoomed in that far. This, you can just see the curve there, but if I zoom in even further, it's pretty straight there too. And when I'm zoomed right in, this function is almost flat, straight, not flat, but straight everywhere. And so I can use my ideas about average slope for a straight line to approximate what's going on with this one. And so that's the idea of a derivative. A derivative is what the average slope is nearby to this point if I'm very close to this point. With this zoomed in window, that's the idea. This slope here is the slope of the curve here. Okay. So we need a formal way of writing that down, and it's called differentiation by first principles. What we're going to do is we're going to go zoom in right on this point just here. Here we are zoomed in. We're going to go a little bit in the x this way, a little bit this way. We're going to figure out the average slope, and what we're going to do is make sure that no matter how which direction I go, if I'm very close, it will be approximately the same as I'll figure out what that approximately is if I'm very close. So let's see. I think I need a whole new page for that. So I'm going to sharpen my pencil. Okay, so just a second, I just need to make sure that we're aware of this. The phrase the derivative is the formula that tells you what the slope is at the moment, and differentiation is the process that creates it. So I might even just write that down. The derivative of f of x the rate of change of f at x. So we say at x, what we mean is very close to x. Okay? And differentiation is the process that finds a derivative. So we used to talk about average rates of change, and now we're able to talk about the rate of change at a particular point, which is technically also an average rate of change, but when you're very close. Okay? So what we're going to come up with very soon is at the moment we're still thinking about it in terms of changes in y and changes in x. That's fine. But what we're going to come up with very soon is we're going to come up with just a straight up formula process that when you look at the way a function's written, you can just write down the formula that tells you its slope at various points. And Newton and Leibniz back in the 1700s, I can't remember which one, but 400 to 500 years ago, figured all this out. And we've worked on it in the intervening time, and people have been learning it in schools for several hundred years. So, okay, so differentiation is the process that finds the derivative, and then differentiation by first principles is the one that's based on average slopes. And so it's easiest to do through an example, and so I'll do it through an example. find the derivative of f of x, which I'm going to say is x squared minus 5x, the one that we had on the screen before, using first principles. And first principles is all this stuff I've described. Okay. So how would you do that? Well, first you're going to want to pick a very small distance, and what most people use is the distance h. It's strange because h you would think is a height, which is a change in y, but most people would use the change in, pardon me, would use the change in x, sorry, h is a change in x. Okay, so we're going to say choose a small number h, right? Which may be positive or negative. Okay. And so the picture that we're going to have in our head is that we have the graph, which looks like whatever it is, and here is the x coordinate. We're going to move just a little bit, one way or the other. So if we move just a bit positive, we're going to do that, and we're going to find the slope of this line, which we know is approximately the slope of the curve too. As long as we zoom in far enough. So as long as the h is really close to 0, it'll be good. Okay. And choose delta x to be equal to h. Okay. So that is find the average slope between x and x plus h. Okay, so this is the whole process of differentiation by first principles. So it's all there. If I ask you, or anyone asks you, to do differentiation by first principles, you can do this. And you need to include these steps. Okay, well, the average slope between x and x plus h is, well, f of x plus h minus f of x divided by, well, h. So let's see, the change in f of x over the change in x is f of x plus h minus f of x over h. Okay, because that's what delta x was. And then I do some algebra until I get to a point where I know what this is. So let's see. F of x plus h is what I get when I put x plus h into this formula instead of x. So I will have x plus h squared minus 5 of x plus h. Need a bit more space than that, eh? Just come back here. X plus h squared minus 5 of x plus h. Okay. Minus x squared minus 5x, all divided by h. You know what, that dividing by h is going to be there the whole time. So what I might do is not actually include it every time and just leave it like this. And just change my working to be about f of x plus h minus f of x. So it's very important that I actually, since I'm not including the h, it's not actually equal to delta x over delta h anymore. So I can't just leave a straight up equals there if it's not the same thing. But what I can do is pull out this bit and say, well, that bit is equal to this. And so when I keep doing some working, I guess I'll just expand things out, eh? So x squared plus h squared plus 2xh. Now that's a shortcut for expanding out squares. You can't just do x squared and h squared separately because technically x plus h squared is x plus h times another x plus h. And so you'll get x times x times h times x, and h times h. So that's where this 2 came from here. And then minus 5 times x is minus 5x, minus 5 times h is minus 5h. And then this bit here, that minus is going to apply to both of these, so I'm going to get minus x squared plus 5x. Oh, that's cool. There's a minus 5x here, and there's a 5x there. They'll cancel out. Okay, let's see. X squared, there's another x squared. Oh, and the x squared and the minus x squared, they'll cancel each other out as well. That's kind of nice. And so what have I got? I've got a 2xh minus 5h plus h squared. Okay, cool. So I've figured out what that top line is. And so now what I'll do is I'll say so, and I can go back and actually get back to figuring out what delta f over delta x is. So let's see, that should be 2xh minus 5h plus h squared, because that's what I just figured out, all divided by h. And I'm capable of dividing everything separately by h now. We get 2x minus 5 plus h. Beautiful. And so this is what it works out to be. If I choose a distance of h away from x, then this is what the delta f over delta x looks like. And the whole idea of this process is that if I zoom in very far, it will be approximately the correct slope. And I'm looking for a formula in terms of x for what that slope is. And so, well, if h is very close to 0, this is going to be 2x minus 5, roughly. And so that's what I can do. I can just send the h to 0. So now I can say, as h goes to 0, whoop, not infinity, as h goes to 0, delta f over delta x will go to 2x minus 5. So that's what I get when I sub in h equals 0 at this stage. This moment, when I divide by h, is really important because not until the h is not on the bottom of the fraction can I sub in h goes to 0. Because if h is 0, I'm not allowed to divide by 0. So I'm not allowed to see what happens when h is close to 0 until after the h is gone from the denominator. And so therefore, the derivative of f at x, so this dash here, most people pronounce this aloud as f dashed x. Some people pronounce it as f prime x, where the prime means first. So the first time I've done the derivative, f dashed x, but technically it's supposed to be the derivative of f at x comes out to this formula. This is called differentiation by first principles. It's designed to follow the process of reasoning that got us to the point where we could imagine calculating a derivative. There are, of course, other ways to calculate derivatives, because we've been doing derivatives for several hundred years now, and so we've learned that some of these things just turn out to have certain answers. You may notice that this minus 5 followed through from the original minus 5 in the formula, and that always happens. It's interesting to see where this 2x came from, actually. It came from this squared here, that you end up with a 2 in the middle when you square things. So it looks like an x squared is always going to produce a 2x like that. And we can use some of those rules that people have figured out before us to skip having to do all this first principles stuff every time. Okay. So I just want to point out one more thing. The notation for derivatives is a little bit funky, and I really should have said this back earlier before I did this example, I'm sorry, but I'm going to do it now. So just some notation. If your function has a letter name like y or p or whatever it is, like p for the population of rats, then we have a notation for derivatives that goes with that situation where we don't have a letter name f of x. And there's a situation where if you've already called it f of x, you can do the dash. So just some notations. So if you have a function f of x equals, formula involving x, then the derivative of f at x is denoted f dashed x. But on the other hand, if you have something like y equals formula involving x, then normally, and then it'll normally be a formula, right? It'll be equals something involving x. Then of f at x is usually denoted as dy on dx. So this d stands for difference as well. It's a difference in y divided by a difference in x. It's just that when the difference in y and the difference in x is really, really tiny, this is what I get. So it's by analogy here. This delta f over delta x and this dy over dx are similar. This is the average rate of change for a size of x that we can figure out what this h is. And this is what you get when you make the h go to 0. And so this clunky triangle delta becomes a nice smooth d. Interestingly, in history, the d was invented first and they put the delta in afterwards when they were trying to figure out how to define derivatives in the first place. But that's where we are. Okay? Sometimes we might just write y dashed. And sometimes we might want to go the derivative of f. And so I just want to point out that there is one other thing, notation, that we tend to use, and it's a particularly sloppy notation. Okay? So this dy on dx, not the derivative of f, sorry, it's the derivative of y. This dy on dx is pronounced the derivative of y at x. Okay? And some people pronounce it the derivative of y with respect to x. Okay, so if you want to say, well, I've just got a random function that's not equal to y, it's not equal to f of x, and I just want to do the derivative of thing, if I have a formula involving x, it could be a formula involving t, and I would do something on dt. If you have a formula involving x, and it's not called y or f of x, then what you need to do, if you don't want to call it y or x, you could actually write down, let y be equal to this formula. That's probably the best way. But what you can do is this. You can say of this formula is d on dx, and then in brackets you put the formula. Okay? So this d on dx is sort of pulling apart the action of doing the derivative at x. And so if you wanted to read it aloud, it's like the derivative at x of the formula. Because it's sort of reading this as the derivative at x of y. And so it's sort of pulling the y off of that and treating it as if it was multiplication, which is a very horrible thing to do because it's not multiplication any more than f of x is multiplication by f either. It's just a thing to do. Okay. So now that we know what it really means in terms of rates of change, and if someone asked us to do differentiation by first principles, we could do it. It might be wickedly more complicated than that, but we can do it. Now that we know that, we can now look at those rules that people developed over the last several hundred years so that we don't have to do this whole process every time. So what we've learned through this process is that there are various rules that derivatives work by. And there's a classic kind of function that we definitely know what the answer is every time. So I'm just going to write down rules. Rules for derivatives. So the rule goes, the first rule is the most fundamental rule, and it was the first one to ever be figured out, and people call it the power rule. and the power rule goes like this. If your function is x to the power of number, then, well, you multiply by the current number power, the current exponent, and put the exponent down by 1. So it goes if f of x is x to the power of number. So this is literally the letter x, or whatever the variable is called. This is a constant. It doesn't change when x changes. Then f of dashed of x, the derivative of f at x, is multiply by the current power and subtract 1 by the current exponent and subtract 1 from the exponent. This is the power rule. It is the most fundamental rule, and it applies to anything that can be written as x to the number. So, for example, f of x equals x cubed, then f dashed x would be equal to 3x squared, because you would multiply by the current power, and then the power that you do, the exponent that you do have would go down by 1. Okay. Now that's great. It'll work for x squared, it'll work for x to the 7, it'll work for x to the 15, it'll work for x to the 1. Okay. But it'll even work for things that can be rewritten as powers. So my first example is, and I'm going to try and use all the different notations. If y was equal to, say, the square root of x, then if you can rewrite it as a power, then you can do it. So I can say, just a second, the square root of x is the same as x to the power of a half. And you'll notice that I've just got a floating equals here, which is saying that this thing is equal to the thing above it. So I don't have to rewrite the y equals, because the reader can tell that this is the same as it was before. And in fact, not putting a y there just makes it easier for them to see that it's just all the same thing. You don't have to keep reading it to say, oh, it's y, oh, it's y, oh, it's y. You don't have to keep writing the same thing over and over. Just the same as I did back here when I did this calculation. These are all the same thing, so I just had an equals here. Okay, so now that it's written as a power, I can do it. So the derivative at x of y is, well, multiply by the current power and put the power down by 1. And if you go down 1 from plus a half, you get minus a half. Now, x to the minus a half is 1 over root x. Because the minus makes it 1 over, and then 1 over x to the half, and then the x to the half makes it root x. And so this is a half of 1 over root x, which is 1 over 2 root x. Now some places that you might look online will just directly give you a rule for doing roots, to go straight from here to here. And it's okay to do that, it's just that most people just can't be bothered remembering that other rule when they can use powers. So one more example of using this power rule. Let's do the third notation. Let's do d on dx of 1 on x squared. Okay, so 1 on x squared, I can rewrite that as a power of x if I want. Now this is an interesting way of doing this notation. It actually makes it a little harder to do the working. If I'm going to work on this 1 on x squared, I'm going to need to change it without moving the d on dx, because I haven't done the derivative yet. So I'm going to have to leave that there because I haven't done that bit yet, and rewrite this as x to the minus 2. So 1 over x squared is the same as x to the power of minus 2. And x to the power of minus 2, well, when I do the derivative of that, it will be multiplied by the current power and put the power down by 1. So that exponent of minus 2 went down to minus 3. And I know that x to the minus 3 is the same as 1 on x cubed, and so I get minus 2 on x cubed. Now some people are able to skip straight from here to here, and that's okay. Okay, so that's 3 places that I can use the power rule. Anything that can be rewritten as a power, 1 over something, or roots can be rewritten as powers, and I can use this power rule. Now I really should have mentioned 2 sort of very simple rules before I got to the power rule, I'm sorry. But I'm going to do them now. These are sort of special cases of the power rule. So let me just go back and do 0 in my rules for derivatives. So rule 0, multiples of x and constants. Okay, so this is even before we got to derivatives. We knew right back when I started talking about derivatives what the slope of a linear function was. We knew that it was just the number attached to the x, and that's still true. If f of x is number times x, so this is a constant number, it's not allowed to be a formula involving x, it just has to be a proper number, then the derivative is just that number. It's always that number, no matter what x is. And, so that's the first rule, if f of x is just a constant, this arrow thing is probably not good maths notation. I should probably say where a is a constant number, then f dashed x is just 0. Just going to draw a picture of that. If it's always, well, I don't even need a picture, but I can do one. If f of x is always the number a, no matter what x is, makes no difference what x is, it's always a, then if I change x, this number doesn't change. So there is no change. It's 0 change when I change x. That's why it's 0. But from a line point of view, y equals a is a horizontal line, and it doesn't have any, it has 0 slope. It doesn't go up or down, it stays the same. Okay. I should point out that if you have f of x equals x, then that's the same as 1 times x, and so the derivative is just 1. Okay. So what's the next thing? Well, the next thing is that if you multiply anything by a number, then that number will still be there multiplied on after you've done the derivative. So the next rule, rule number 2, sorry I had to go back and do 0 before I'd done number 1. I've called them 0 because it's like, well, these are even earlier than even figuring out what the derivative is. So number 2 is going to be constant multiples. So if you have a constant multiple, then the derivative of your constant multiple is the constant multiple of the derivative. Okay, so most people write it like this. If f of x is constant times g of x, for constant a, then f dashed x is a times g dashed x. But that's a little hard to actually process most of the time. It's actually a lot easier for me to just remember that if there's a constant multiplied on before, then there's still that constant multiplied on after. So in my head it's if there's a constant multiple, it's still there after. Okay? So just as an example, if you had y equals, I'll just do it with the f of x actually. If you had f of x is equal to 5x to the 7, right? Then according to this rule, this constant 5 is multiplied on. It will still be there afterwards, multiplied on. And then I can just do the derivative of this bit, 7x, and the 7 will go down to 6. So without the 5, the derivative would be x to the 7 would go to 7x to the power of 6. With the 5, 5 multiplied on before, still 5 multiplied on after. And so that will be 7 times 5 would be 35. Okay. One last rule before we move on to anything else. We're almost at the stage where we can do quite a few nice derivatives. Number 3, addition. If I might call this one h if that's okay. No, if f of x is g of x plus h of x, then f dashed x is g dashed x plus h dashed x. Basically meaning addition means you can do, that does not look like a can, means you can do derivatives separately. So using all these rules together, means you can do derivatives separately. Using all these rules together, if you have anything that is a combination of various powers of x, then you can do the derivative. So you ready? I'm going to do some proper examples now of stuff that we can actually do. If y was equal to x cubed plus 5x minus 7, for example, then the derivative at x of y, well, 3x, and the 3 would go down to 2, that's great. The 5, well, 5x just becomes 5, and constants become 0. That's great, and the plus just meant I could do those two bits separately. Let me do it as a function. Let's mix it up. Let me call it k of x. Seven x to the power of 6 minus 8 over x. It's a wickedly weird-ass function, but I can do it. So when I do the derivative, so let me point out something that you may not have noticed at this stage. Every time I do a derivative, I have not just put equals. Okay? Y is equal to that, and it's totally not equal to this. That's the derivative. So I have to tell the reader that it's the derivative that's equal to this. Very important to make sure your equals does only ever mean actually equal. Okay, so if k is equal to this, then k dashed x is equal to this. So the 7 will still be there because it's multiplied on. The 6 will become 6x and the 6 will go down to 5. Oh, poo. This would have been way easier to do if I had done the derivative, if I had rewritten it as a power first. Okay. So this original thing is still equal to this, and 8 times 1 over x is the same as 8x to the minus 1. Right, now I can do the derivative. So you see this equals is okay because this is still equal to the original thing. So 7 times 6x to the 5 minus 8 times minus 1x, and the minus 1 adding another minus 1 would go down to minus 2. So I've got 42x to the 5 plus 8x to the minus 2. And if I really felt in a good mood, it's tradition to not have negative powers, negative exponents anywhere in your description. You might notice that I keep saying exponents and powers, and I'm trying to be very careful. Exponent is the name of the number that's up here. Power is the whole thing together. So, okay. And this working is very nice working. Kx is this, and these are different options for what Kx looks like. K dash x is this, and these are different options for what K dash x looks like. Now I should point out that if you were given just a straight up function and you were told differentiate this, the easiest way would be to give it a name. So I'm just going to do one more example. Differentiate 3x squared plus x over x. Okay? So if I was going to do that problem, it's going to be way easier to do this if I give that 3x squared plus x all over x a name. I could call it fx, f of x, or I could call it y, or I could call it, w, or any other letter I want, or g of x. But as long as I give it a name, it'll be easier to write down. So why don't I do that? Let g of x be equal to this. Okay. And then I need to, the only rules I have at the moment are to rewrite things as powers. So I know that dividing by x is the same as multiplying by 1 over x, and multiplying separates out over plus. So I am able to apply this division to both of these things. If I have plus divided by a single thing, I can do each of them separately divided by that. So 3x squared divided by x is the same as 3x, and x divided by x is the same as 1. And now I can do that derivative. The derivative of 3x is just 3, and the derivative of 1 is 0. That was a lot easier than I was expecting it to be. Ah well. Okay. So those are the first rules. The first rules of derivatives are that multiples of x and constants, multiples of x become the multiple, constants become 0. Powers multiply by current exponent and put the exponent down by 1. And constant multiples will still be there afterwards, and two things added together, you can do them separately. And that allows us to do quite a lot of stuff, and even some stuff that doesn't look quite like it's possible is possible sometimes to rewrite it in that format. But what if you have things that aren't like that? Okay, what if it's more complicated? And we've already seen two things that you can do to functions and what happens to the derivative then. You can multiply by constants, and you can add things. And I should point out that even here, technically this is a subtraction, but look, subtraction is the same as multiplying by a negative anyway, and so the rule still applies. But what if you had two things multiplied together? Okay? So what if there were two things multiplied together? Now I could do a similar trick to this. If I had two things multiplied together, I could always expand out the multiplication and turn it into something that was powers and differentiate that way. That's great. But what if I couldn't expand out the multiplication? What if it was like a half power that doesn't expand out? What if it was something to the power of 72 where it's going to be wickedly hard to expand out? Well, that's the sort of thing that we have a rule for. It's called the product rule because it goes with things that are multiplied. So what number was I up to? I think I was up to number 4. Lots of people order these differently, so it's not like you can just say, I used rule number 4. You should say, I used the rule for addition. Though most of the time, if you're actually calculating derivatives, no one actually cares if you tell them what rule you used. So if you use the product rule, someone who knows how derivatives work will be able to look at your work and say, oh, right, they use the product rule. You don't have to tell them. Did I do these in capitals before? No. Okay. So product is the fancy word for the answer you get from a multiplication. In the general English sense, it just means thing that is produced. And back in the very early days of mathematics, like in the 1200s, product was used, like the product, the only fancy answers that they could calculate were multiplications anyway, and so they're all called products. And so product means multiplication in this context. So it's the rule specifically for when two functions are multiplied together. And it's a bit complicated actually. It goes like this. If f of x is made by multiplying two functions together, so this is a dot as a fancy way of doing multiplication. Sometimes you won't even see it there, they'll just be written next to each other. Then what you're going to have to do is take into account both pieces. And what it's going to produce is two separate bits that are going to be added together. You can't just differentiate this one and differentiate this one and multiply them together. That's just not how derivatives work. Okay, both of these are going to affect the outcome separately. Alright, so the way it works is this. Then the derivative is you're going to have to differentiate one and keep the other. And you're going to have to keep one and differentiate the other, and you're going to have to add them together. So the sort of idea is that, well, if you're changing both g and h, you could do an experiment where you change g by a little bit, but you don't change h, and that's this one. And you could change h by a little bit and don't change g. Because if you don't change the h, it sort of counts as a constant that's multiplied on, and so it won't really make a difference to the answer. And if you sort of just change the h, then the g counts as a constant that's multiplied on, which is what would happen here. But it's not really either of those things, so we can just add them together. And the whole thing works out because you're just looking very, very close to the functions, and it works out okay. And anything that's not quite right, well, it's approximately 0 anyway. There are some really cool explanations of the product rule, but I'm not actually going to provide them today. Feel free to go and have a look at other resources online. So that's the product rule. And we can apply the product rule anytime there's two things multiplied together. So for example, if we have y equals x plus 2 no. Not that. Oh yeah. So this thing here, totally, there is nothing stopping me at all from multiplying all this out. You know, x squared times x cubed, x squared times 7x to the 8, x squared times 6x times 6, 3x times x cubed, 3x times 7x to the 8, 3x times 6 minus 5x cubed minus 5 times 7x to the 8 minus 5 times 6. And that'll give us all these different bits, and I can do the derivative of every bit separately like I've already done, and that's perfectly acceptable. But another way of doing it is to avoid expanding it out and do the derivatives separately the way the product rule works. You can't just do one derivative and the other derivative and multiply them. We're going to have to do this funky combination here. So I'm going to need to do the derivative of this and keep this, and then I'm going to have to keep this and do the derivative of this, and I'm going to have to add the answers together. And for the purposes of making this a little easier to write down, I'm going to use that d on dx notation. I'm going to do the derivative of this, and I'm going to keep this, and I'm going to do the derivative of this. I'm going to keep the first one, and I'm going to do the derivative of this. What you aren't allowed to do is just write this and then later do the derivatives, because it's just wrong. It's not the derivative yet. If you can separate it out and do some working separately, and I'll show you how to do that in a little while. But for now, I just wanted to show you how the product rule works. And so this derivative is 2x, the x squared becomes 2x, 2x to the 1 technically, and the 3x becomes just a 3, and then I keep this bit. And then this bit becomes 2x, no, not doing the derivative of that bit. This bit's staying the same, there's no d on dx on that bit, so I keep that as it is. And then this has to be differentiated, so the x cubed will become 3x squared. The 7 is still there because it's multiplied on, 8x to the 7. And that 6 will go away. And this is the derivative here. You could, if you felt inclined, expand it out now, but the whole point of this process today was to not expand it out. It is tradition to try and expand things as far as we can, but you know what, I just can't be bothered. I might possibly just figure out what that 7 times 8 is. 7 times 8, 7 times 7 is 49, 56. Okay, so I'm just going to stop there. I'm not going to go any further. It's okay to not go any further in some situations. Most of the time we'd prefer you to simplify it because you might want to do something else with it afterwards. That's how the product rule works. Rightio. I'm going to come back and use the product rule again in a minute, but I just need to do another example first. What was I up to? 5. Well, we've done one for multiplication, and product means multiplication. So I'm actually just going to write that in for multiplication. What about one for division? Well, the quotient rule is for division. It would be really nice if we just had like the derivative rule for division, but no, sorry, it's called the quotient rule. There's nothing we can do about it now. You can call it derivative rule for division if you like. So the quotient rule, well, division is a bit complicated. You can actually completely avoid the quotient rule, but not until you've learned the rule after this. So the quotient rule goes that if f of x is two things divided by each other, then the derivative, all right, here we go. We're going to have the bottom squared. Just trust me. It's to do with the fact that this is something to the power of minus 1. And then on the top, we're going to have the bottom and the derivative of the top. And then we're going to have the derivative of the bottom and the top. And a minus. That's the order that I remember it in. You might find something more productive. Some people remember it as bottom d top minus bottom d top minus d bottom top over bottom squared. I remember it is like the product rule, but with a minus, and the top line and the bottom line both start with an h, not an h dashed, or you know, or a u over v, or a p over q, or whatever you want to call it. People will use all sorts of different letters. It's the positions that they're in that's the important thing, not what letters they are. So please, if you're talking to someone about this, don't say, hey, what's your g and what's your h? They won't understand it. Or even if you say, what's your u and what's your v? You're going to need to say, what's your numerator and what's your denominator? Numerator is the name for the top and denominator is the name for the bottom. So just as an example, now if I was going to do this, I would attempt to see if I can write that as something nicer, but I just can't. It's okay if you have a plus on the top and a single thing on the bottom to divide them separately, but that's just not how division works when there's a plus on the bottom. There's nothing I can do. The only thing I can do is the quotient rule, really. So what I'm going to do is I could, if I wanted to, I could do the quotient rule all in one go without writing anything else down if I want, but I could also tell the reader what all the pieces are. So I could say something like, let h of x, g of x is bx squared and h of x bx plus 1, like that. And then g dashed x is 2x and h dashed x is, well, x plus 1, the derivative of x is just the number next to x, and the number is really a 1. Okay? So f dashed x, so f of x is g of x on h of x. Maybe not so, we can say. Now it's this, so therefore f dashed of x is h g dashed minus h dash g over h squared. It's okay to leave out the brackets on the x if you want to shorten it a bit. Now what was all these things? H was equal to x plus 1, g dashed was 2x, h dashed was 1, g was x squared over x plus 1 squared. Okay. And it is useful to sort of try and simplify a numerator. It's almost never a good idea to expand out a denominator, so I'm just going to leave that as it is. So let's see, x plus 1 times 2x. So let's see, x times 2x is 2x squared. 1 times 2x is 2x minus x squared, which is just x squared plus 2x. And that's the best I can do. Now I should say something. I didn't have to go through all of this work to do the quotient rule. I could just as easily have done this, you know, and just gone straight to bottom times derivative of top minus top derivative of bottom times top over bottom squared, and that would have been perfectly acceptable to do, and then I would still have done the same working. Okay, you are allowed to do this with the quotient rule, but if your quotient rule is particularly complicated, it might be useful to do something like this. Okay, product rule for multiplying, quotient rule for dividing. What if there is one more thing that we can do to functions, and that one more thing is you can put one function inside another. So this is our last rule. Here in South Australia, it's called the chain rule. And it's for composition. And the action of composition is doing one function, subbing one function into another function. Okay, so the chain rule goes like this. If one function is inside another function, then you can do the derivative of the outside function, keeping the inside as it is, multiplied by the derivative of the inside function. So if f of x is equal to g of h of x, then f dashed x is g dashed. So you do that as if the h of x was just an x, and you keep the h of x as it is, and then you multiply by the derivative of that. And the reason it's called the chain rule is that we end up with two derivatives multiplied by each other. Okay, so let me do an example of the chain rule. So an example of the chain rule would be something like, let's call it mx today, because I feel like having a whole different letter that we haven't used before. So let's say that m of x is like I know it's stupid, right? But it's x cubed plus 8x squared all to the power of 17. So what I can see here is that there is some function subbed inside another one. That if that had just been an x, it would have been x to the power of 17. and then this other function is subbed inside. So most people, when they do the chain rule, don't write out what any of these functions are called. They do this. So I'm going to pretend that that is an x. Okay, and if it was just an x, I would multiply by the current power, and I would put the power down by 1. But it's not just an x, it's an x cubed plus 8x squared. So I have to put that in here. So this thing that was here is still here. I just treated it as if it was just an x. But I can't just do that. I have to also multiply by what I get when I differentiate this. So I'm going to have to do the derivative of this. And the derivative of this is 3x squared plus 8 times 2x. Because the 8 is a constant multiplied on, and I'll have to do 2x. And so I get 17 3x squared plus 16x x cubed plus 8x squared to the 16. Now there's absolutely nothing stopping me from keeping it in the order it was. It's just tradition to have the highest powers at the right hand end, that's all. And that's how the chain rule works. Okay? It is possible to write this another way. I could have, and this is another way of doing it if I wanted. I'll do another example and I'll write it a different way. I'm favouring 8s today. Now I'll just do an ordinary power. Now there is nothing stopping me expanding this out. It's just x to the 5 plus 3 4 times, but it's a bit complicated. So I can use the chain rule because I have a function inside another function. What you can do is you can give these functions names. So if this was called f of x, I would normally say that this was h of x and that was g of x. And it's tradition to just use the letter you've got. But what most people do is to call this u, because it's like a y without a tail, so it's a related sort of letter, and write the working this way. So they'll say, okay, let u be equal to this thing inside. Okay? So then you'll notice, so that y is equal to u to the 4. Okay? But that u is really secretly a function of x. So we're going to say that the derivative of y should be the derivative of this outside function times the derivative of the inside function. So we can figure out what the derivative of this is. So most people would write it like this. Now dy on du is 4u3, because we'll multiply by the current power and put the power down by 1. And du on dx is, let's see, we had an x to the 5, so 5x to the 4. Okay. And then the 3 went away because it was a constant added on. Okay, and so according to the chain rule, we should have the derivative of the outside function, which is the dy on du, times the derivative of the inside function, which was the du on dx. And so therefore, dy on dx, which was the goal, is the derivative of the outside function times the derivative of the inside function. And that is 4u cubed times 5x to the 4. But the u is really x to the 5 plus 3. So I suppose we could multiply that 4 and the 5 to get a 20. Now I did say you normally put the highest powers at the end, but really you put the most complicated thing at the end. So if there's a big bracket with stuff in it, you normally put that at the end. So this is an alternative way of writing the working, if you like. You could have as well said, if this was called f of x, say, well, this is h of x and this is g of x, and done the g dashes as well. Okay. So I'm just going to give you one more example of this sort of thing. Possibly two more, of combining all the rules together. So I'm just going to put a line here. So it is possible that you might want to combine several of these all at once, right? And use the chain rule and the product rule at the same time, for example. So let's do one. Find the derivative of, let me do one. That. X plus 8 root x plus 3 to the 7. I mean, it's a stupid, stupid function. It's totally possible to expand it out, but that's what we've got. Okay. So most of my examples haven't been literally as an example that you might see in a set of notes. But I did want to do this one just so that you could see how it works from an actual perspective of seeing an exam or an assignment and giving it a go. So find the derivative of this. Well, I need to give it a name. And I find it productive to call it f of x. It's a little easier to write. So let's say let f of x be equal to x plus 8 root x plus 3 to the 7. Now I can see it's made of two pieces. There's this bit and this bit. Okay. And I can see that this bit has a thing inside something else. And so I'm going to have to use the product rule because there's two bits multiplied together, and the chain rule because there's a bit inside something. So it might be easier to give these things names. So let g be x plus 8 and h be root x plus 3 to the 7. Now in order to differentiate that, it's going to be easier to write that root x as an x to the half plus 3. Okay. So g dashed is going to be 1. So the derivative of x is the number next to the x, which is a 1. The derivative of 8 is 0. H dashed, I can use the chain rule. So if this bit here was an x, I would go 7 times the x to the power of 6. But that thing is not an x, it's an x to the half plus 3. So I'm going to have to multiply by the derivative of that. Now x to the half will be half of x to the minus a half, and the derivative of 3 is 0. And so I get that. So just because it's easier, I should probably figure that out. The 7 times a half is just 7 over 2. The x to the minus a half is 1 over x to the half, which is 1 over root x. And so it looks like I'm going to get 7 over 2 root x times... I can probably put the half back here now, because it's tradition to put it back in the format it came from, and it didn't have half powers before. Okay, so f of x is g times h, which means that f dashed x will be g dashed h plus g h dashed, and g dashed was 1 and h was root x plus 3 to the 7, and g was x plus 8. Oh, I'm not going to have space. G was x plus 8, and h dashed was 7 over 2 root x plus 3 to the 6. Whoops, sorry. Which is that? Not pretty, but there it is. I could probably attempt to do something nice to it, because this root x plus 3 to the 6 Well, they're both here, so let's give that a go. They both have a root x plus 3 to the 6. That leaves behind a root x plus 3 to the 1 here, and it leaves behind an x plus 8 times 7 over 2 root x. It's not really that much better, is it? Let me try one more thing. So root x plus 3. I can multiply this by that. So 7 over 2 is still going to be there. And x divided by root x is root x. I'm going to get a 56 over 2 root x. Yeah, it's pretty awful. I really should have left it the way it was before probably, but I'm committed now. 7 over 2 plus lots of root x plus 1 lot of root x. 1 lot of root x is 2 over 2, which is, so we get 9 over 2 root x plus 3, and 56 divided by 2 would be 25 plus 28. All right, well, not too bad. Not too good either, but it was pretty yucky to begin with, I suppose. So one more thing. I do have just enough time before my recording time runs out. One more thing to say is that the chain rule can be used in a chain with one piece inside another piece inside another piece. So let me do that. I won't call it QX. Today I shall call it Y. Okay, so what if I had a chain of things that are all inside each other, with bits and pieces inside other bits and pieces? So what if I had a great big root something like that. It's awful, right? But not that awful for differentiating purposes. I notice that there is something under the root, so already as a chain rule thing. And I also notice that, let me just change what this is, make it a squared. I also notice that there's something inside the x to the 5. Actually, I'm not going to make it a squared. I'm just going to leave it as an x. Okay, so watch. I'm going to need this to be written as a power in order to do it. Okay, so according to the chain rule, I can differentiate this as if it was an x. So it will become a half of thing to the minus a half. But the thing is x plus 3 to the 5 minus 8. And now I can just ignore everything else and focus on just this bit. Now the derivative of that, well, it would be 5x plus 3 to the 4 minus 0. But now there's another derivative on the inside of this. And actually, do you know what? I will... and the derivative of x plus 3 is 1. So you can do this as long as you like, and you can just keep pulling out the next bit and doing the next derivative as you go. So 5 on 2x plus 3 to the 4 times x plus 3 to the 5 minus 8 to the minus a half. And if I really wanted to put it in the format it was originally, the 5 can stay on the top. So we've got a dividing by 2, so that will end up on the bottom of the fraction. And we actually have a minus a half, so that'll be like this. Not pretty, but there it is. So those are all the rules. I do have a handy little handout somewhere that I will put a link to at some point. And I can summarize all those rules. But ultimately, remember that this is used to find how quickly a function is changing at certain points. I'll need to do a whole separate seminar on the concept of finding tangents. Thanks.